in the next hour. So after the first session, we get David Kenny, General Manager IBM Watson, who's going to reveal a few interesting things. But to start with, a man who is co-founder and CEO of a business that Google bought a couple of years ago for £400 million, I've reported, building general artificial intelligence, which is the big one. Please welcome, to tell us a bit more about some specific applications before we have a deeper conversation, Demis Hassabis of Deepmind.
Hi everyone, it's really great to be here. So, as David said, I'm going to be talking about general artificial intelligence, and I'm going to talk a little bit about the latest work that we've been doing, and then talk at the very end about some of the applications we plan on. So, first of all, Deepmind, as David was saying, we founded the company in 2010, and then a couple of years ago we joined forces with Google to sort of turbocharge our mission. The way we think about Deepmind is a kind of an Apollo program for AI. So we have around 300 people and more than 200 research scientists. And one of the things that we're trying to do here is to find a new way of organizing science, to try and combine the best from Silicon Valley style startups and the best from the top academic places, and actually combine that together into a unique culture that allows us to make research breakthroughs faster than ever. So our mission, where we articulate it, is in two steps. Step one, to try and fundamentally solve and understand intelligence. And then if we can do that, we believe that we can use that technology to try and apply it to almost everything else. So we actually feel that artificial general intelligence could be one of the most important technologies that humanity ever invents. And that's why we work so hard, and I spent my whole career working on this project. So how do we do that more prosaically at Deepmind? Well, we try and build general purpose learning algorithms. And so what does that mean if we break that down? So all the algorithms that we work on at Deepmind have two things in common. First of all, they learn automatically how to do things, how to master tasks, directly from raw inputs and raw experience. So they're not pre-programmed or handcrafted in any way. The second thing is that the idea of generality. This is the idea that the same system or same set of algorithms can operate across a wide range of tasks, including new tasks that the algorithms have never seen before, and operate correctly in those new environments. So we call this kind of AI artificial general intelligence. And the hallmark of AGI is that it's flexible, adaptive, and potentially even inventive. So it can come up with things that the programmers themselves didn't know how to do, because it's directly learning for itself how to master these tasks. If we compare that to most of what's called AI out there at the moment, which we call narrow AI at Deepmind, most of the AI that you interact with every day is actually of a different sort of AI. It's handcrafted, and especially a special case for one particular task. So because of this, most of the AI that you interact with today is quite brittle. If you do something that's unexpected, that the programmers didn't cater for, there's no way that the AI can deal with that unexpected event. And of course, humans are very unpredictable in the way that they use devices. So there's always something unpredictable happens that the programmers couldn't cater for beforehand. So we think this is a big problem in AI, and why we work on these kinds of general learning techniques. So probably still the most famous example of a narrow kind of AI is Deep Blue, IBM's Deep Blue, which famously beat Garry Kasparov in the late 90s at chess. And it's an incredibly impressive feat. But Deep Blue itself was only built to do one particular thing, play chess. It couldn't even do something much simpler, like play a much simpler game like noughts and crosses, without being totally reprogrammed from scratch. So nothing in that knowledge base that IBM had, that Deep Blue had about chess, would be useful for anything else. So this is a classic case of a narrow kind of AI. Now after Deep Blue beat the world chess champion, the next kind of holy grail or grand challenge for AI research in games was another game, a much more complex game called Go. Now I'm going to talk, the rest of us talk about AlphaGo, a program that we created very recently and was one of our big breakthroughs, our most sort of recent breakthrough. Now AlphaGo is a program to play this game called Go. Now for those of you who don't know, Go, this is what a Go board looks like. It's a 19 by 19 grid. The board starts empty. It's played between two players, and they take turns to put down these stones, these pieces, black and white stones. And they put the stones down on the vertices of the board. And the idea of the game is to surround your opponent's pieces or surround empty territory. And the player that has the most territory wins the game. Now the rules of Go are very simple, but it leads to incredible complexity. And in fact, Go has a very long and storied history. It's what they play in Asia instead of chess. So it was originated in China 3,000 years ago, and more than 40 million players play it today. And there's 2,000 professionals. So there are professional Go schools that you go to as a child if you live in Korea or Japan or China, if you show promise in the game of Go. And you play Go 7 days a week, 12 hours a day. And one idea of how the sort of complexity of Go, why it's so much more complex than chess, one way to illustrate that is that there are more possible board positions in Go than there are atoms in the universe. 10 to the power 170. So even if you were to use all of the compute power on the planet and run it for 1 million years, you wouldn't have enough compute power to calculate and brute force everything about the game. So this is why trying to crack the game of Go has taken 20 years beyond solving chess, beyond Deep Blue. So the two really big reasons why Go is hard for computers to play is that, as I've just said, the complexity is actually enormous. It's probably, Go is one of the most profound games mankind has ever devised. So from these very simple rules comes this enormous and beautiful complexity. And this complexity makes brute force search, the type of search that was used in Deep Blue, intractable. So you can't use those kinds of approaches that were used for things like chess computers. They simply won't scale to Go. So there's two main challenges if you break it down. One is the search space is enormous, and the second thing that's even harder is that it was thought to be impossible to write an evaluation function for Go to tell the system which player, black or white, was winning in a particular position. So this is incredibly hard for Go. And I'll just delve a little bit deeper to both of those two problems. So in Go, in any particular position, there are an average of 200 possibilities, 200 possible moves. In chess, by contrast, in an average position, there are only 20 moves. So Go has got an order of magnitude bigger branching factor. So that's what leads to this huge number of possibilities. So it's much harder to figure out what you should do next if you're going to consider all the different possibilities. And the second thing is the evaluation function, telling the system, how does the system know whether a position is desirable for black or for white? Well, in chess, the way you can do that is you can handcraft a specific set of rules. You can talk to chess grandmasters, and you can figure out how they make decisions, and then you can codify that in a sort of database with rules. And you can use that database to tell you who is winning the game. Now, that's easy in chess because chess has a concept of materiality. So, for example, if you wanted a first approximation, you can just add up the value of the pieces on the board. So the queen is worth 9 points, the rook is 5 points, the knight is 3 points, and so on. And whichever side has the most value on the board, so first approximation is winning the game. So that's already a very useful heuristic. But in Go, there's no concept of materiality. Every piece is worth the same. Another issue with Go is that Go is a constructive game. So what I mean by that is that the board starts off completely empty, and the position gets built up piece by piece. So the game gets more complex as time goes on. If you compare that to chess, chess is a destructive game. So all the pieces start on the board, and as the game goes on, it simplifies. Pieces are taken off the board. So what this means is in Go, if you want to evaluate a current position in the middle game, you have to involve predicting the future, how the game might go. Whereas in chess, you can assess the current position in isolation. You don't have to worry about the future so much. And the final issue with Go is that very small changes, one piece moving by one position, can actually change the whole evaluation of the position. So very small changes can make a big global difference. So, I just want to take a moment before I show you the program as to how do humans deal with this kind of complexity? Because of course humans play this game to a very, very high level and have been playing it for 3,000 years. And actually Go is thought of as much more of an intuitive game than a calculation game like chess. So top players rely on their instincts and intuition to figure out all these complexities and feel their way to the right move, rather than calculate out the right move like a chess player would. And in this sort of 3,000-year history of Go, very rich history, there's this concept of what's called a divine move. A move so profound that it's not understandable by humans, and it sort of comes from a divine inspiration. And top Go players, 9-dan professional Go players, spend their whole careers hoping to play one move that's worthy of the name. And that idea of this sort of divine move is unique to Go. So how do we overcome these issues and build AlphaGo? Well, we turn to a number of new technologies that we've been using at Deepmind, especially deep neural networks, which are all the rage right now, called deep learning. What we did first is we trained 2 neural networks, and we started off by downloading 100,000 games from the internet, Go servers. So these are games played by human amateurs, strong human amateurs, on Go servers in Japan and Korea. And we trained our first neural network, which we call the policy network, to mimic the behavior of the human players. So we gave it a position, and we told this network, we trained this network to figure out and copy what the human player would do in that position. Now the thing is, of course, we don't want to just mimic strong amateurs. We want our program to be stronger than the best players in the world, the best professionals in the world. So the next stage is we took this first network, and we had it playing against itself millions of times on our servers. And each time, learning through its own mistakes and learning incrementally to make fewer and fewer mistakes with each game. And we used a technology called reinforcement learning to do that, where with each game, it updated its neural network depending on whether it won or lost. And after we have this new neural network, we freeze that network, and we play that final network 30 million more times against itself. And that gives us what we call our goal data set, the final data set that we need. And we use that data set to train a final neural network, which we call the value network here in pink. This is the second neural network. And what this network does is it takes a position, a board position from Go, and we know from the 30 million games that we've played out, who ends up winning the game from that position. And we train this new value network to predict from a particular position who will win the game and by how much. So this network in pink here, the value network, is the fabled evaluation function that people thought would be impossible to program for Go. And what we did instead is we sidestepped that problem by having a neural network learn how to evaluate a position rather than us programming it with the definitions. So we took these 2 neural networks and we applied it together into a search tree. So this first neural network, the green one, takes a board position and outputs probability distributions around which moves are most likely to be played in the current position. So you see here on the green board, the higher the green bar, the more probable that move is. AlphaGo thinks that move is. The second neural network, the pink network, takes the board position and outputs a single real number between 0 and 1, which gives a prediction about which side AlphaGo thinks is winning. So 0 is white, 1 is black, and by how much. So if it's 0.5, it means that AlphaGo thinks that the game is even. And just pictorially, what you can see is this cuts down this enormous search space of possibilities that I already told you as more than the atoms in the universe. So if you imagine that AlphaGo is trying to make a decision at the top of this tree, how is it going to make a decision about what to do next? Well, what it does is it calls these 2 neural networks, the policy network first, the green network, to narrow down the breadth of the search. So instead of searching the 200 possibilities from every position, it only searches the top 4 or 5 possibilities. And And then secondly, it uses the value network, the pink network, to cut down the depth of the search. So instead of having to search all the way to the end of the game to find out who won, it can call the evaluation function at any time to give it an estimate of who is winning. So after we built this AlphaGo program, it was time to test it against the best of the current Go programs, which are built using traditional methods. And we found that AlphaGo won 99% of its games against all these other programs, some of which people have been building for more than 10 years. So then it was time to challenge some of the best humans in the world. So we then took on the European champion, Fan Hui, who is 3 times European champion. He was born in China, became professional when he was 16, and has won the European Championship 3 times. And this is what happened.
After the first game, maybe they don't like fight. They like play slowly. So it's why we begin the second game, I fight. I see, maybe I'm right. It's why, for another game, I fight all the time. Now it's good. Now it's good. But I lose all my games.
So Fan Hui, AlphaGo won 5-0, which is the first time that a Go program has ever beaten a professional. So this is around about a decade before people were expecting, the experts in the field, AI experts and Go experts, a whole 10 years before this was going to happen. So this was published as a front cover article in Nature, and it caused a huge stir in the machine learning community. So in fact, it's one of the top 20 most downloaded papers ever in Nature, which is the top science journal in the world. So then we took our final step, which was to take on the world champion, a South Korean grandmaster called Lee Sedol. He's a legend of the game. He won 18 world titles and is considered to be the greatest player of the past decade. So the way I describe him is he's kind of like the Roger Federer of Go. And we took him on in a $1 million challenge match in Seoul earlier this year in March. It was absolutely a huge event. It was an incredible press conference with thousands of journalists. The whole country came to a standstill, and all of Asia were watching the game. And incredibly, we managed to win 4-1, and AlphaGo won the match, and it was an amazing experience. And we were able to beat this top player in the world by 4 games to 1, which was incredibly unexpected. But not only did AlphaGo win, it played some incredibly creative moves, and I just want to show you one example of those moves. So in game 2, this is the position in game 2, and AlphaGo is playing black here, and AlphaGo on move 37 played this move here that's marked by the white triangle. And I just want to take a minute here to explain to you why this move was so astounding to the Go world and why it was so considered to be so creative. So Go, as I said, has been going for 3,000 years. Humans have been studying this game for 3,000 years. And there are 2 important lines on a Go board. The third line, which is marked here, if you play a piece on the third line, what you're trying to do is capture territory on the side of the edge of the board. Instead of that, if you play on the 4th line, what you're basically saying to your opponent is, you're trying to get power and influence into the center of the board. And for 3,000 years, the received wisdom has been that playing on the 3rd and 4th lines, and exchange on the 3rd and 4th lines is equal for both players. But what AlphaGo decided to do was to play on the 5th line and take power into the center. And this is completely unheard of and against all the principles of playing Go, the known principles of playing Go. So for a professional, this would be unthinkable. And in fact, about 50 moves later, it turned out that this move ended up affecting the fight in the bottom left-hand corner of the board. These two pieces over in the bottom left-hand of the board, so completely on the other side of the board. So this is what the professionals thought about it.
That's a very surprising move. I thought it was a mistake. Well, I thought it was a quick miss, but for an online Go, we call it a put down. Yeah, it's a very sweet. Something like this would be more normal.
So those are the commentators, the 9 down professionals, commentating live on the game. And he was so surprised about the move, he thought that our computer operator had misclicked on the computer screen. That's how astounded he was. And you can see him, they didn't even know where to put the piece. We think that this move 37 is going to go down in history, and famous moves in Go end up getting names and books written about them and all sorts of things down the years. So we feel that this move is being analysed now by the whole Go world for the last 3 months. And of course, Lee Sedol himself then did his own incredible move in Game 4, this move 78, which will also go down in history, and I don't have time to go into today, that surprised the computer, AlphaGo, and he won Game 4 because of it. Again, another incredibly intuitive and creative move. What's really interesting is now the culture impact of this match. 280 million people watched the 5 games across Asia and the rest of the world. 60 million in China just for Game 1. There were 35,000 press articles written about the match during the week of the match. And the thing I'm most proud of actually is there was worldwide, online, there was sold out of Go boards and Go pieces because so many people around the world were wanted to learn and try this great game. Another interesting postscript is that Lee Sedol himself felt that he'd improved because of the match and come up with new ideas. This is a really interesting thing of machine learning and AI helping to improve human performance as well. And since this match, Lee Sedol has gone on an incredible winning streak himself against all his professional opponents. And he said many interesting quotes about how AlphaGo has allowed him to think about new ideas about how to play Go and rejuvenated his passion for the game. So I just want to end here by talking a little bit about intuition and creativity. So, I've talked a lot about Go being a very intuitive and creative game. So what do I mean by that? So one way of operational sort of definition of intuition is that it's implicit knowledge that's acquired through experience, but that's not consciously accessible or expressible. So you can ask, well, if you can't access it consciously, then how can you know that that knowledge is really there? Well, of course you can test for this implicit knowledge, and you can test for the existence of it, the quality of it, by behaviourally testing for it. So for a Go player, you can give them a Go position, and you can see the quality of the move and the output that they decide to play. And that tells you how good their implicit knowledge, their intuition is. What about creativity? Well, creativity I think you can operationalise as the ability to synthesize knowledge to produce a novel or original idea. And I think again, AlphaGo, I feel, clearly demonstrated these abilities, albeit of course within the limited domain of Go. So just to end about the critical difference, circling back to what I said at the beginning between narrow AI and general AI. And therefore, what is the difference between AlphaGo and Deep Blue? Both of these programs beat world champions at their respective board games. But although AlphaGo is a big achievement, the key point here is how we did it. So Deep Blue was pre-programmed with specialised handcrafted knowledge that was distilled from chess grandmasters. Whereas AlphaGo used general purpose algorithms, these neural networks and reinforcement learning to learn how to play Go and improve itself. It's a modular system that combines several different aspects together: deep learning, reinforcement learning, Monte Carlo research. So it combined pattern recognition with planning. And I think that's what we're going to see in the future with AI algorithms, combining the strengths of different types of algorithms. And because of this, AlphaGo thinks and plays in a much more human-like way. So now, because this is general purpose algorithms, of course the aim of Deepmind is not just to play games. We use games as a great testing platform to develop our AI algorithms, but ultimately we want to apply these technologies to have real-world impact on very important problems. And we're looking right now at applying these to things like healthcare, robotics, and conversational personal assistance. Thanks for listening.
Thanks, Dev. It's amazing work. Now, you're a gaming guy. When you were 4, you learned chess by watching your dad play your uncle, and by the time you were 5, you were playing at a national level. But let's be honest, Deepmind isn't really a company about gaming, is it? You're trying to build something bigger. So what is the mission and the purpose of Deepmind?
That's right. So we use games as a testing ground, a proving ground for our AI algorithms, because it's very efficient to test it in games. There are kind of games, the complex games are kind of microcosm of some real-world problems. So if you can tackle it in a game and do that really well at that, then you can maybe translate that to some real-world problems. So for me, the two areas I'm really excited about and passionate about applying AI to are science and healthcare.
So if you're building general artificial intelligence, not just recognizing pictures, translating words, that's a very big project, teaching the machine how to think like a human brain. How many years do you think it will take?
So we think when we set out on Deepmind 5 years ago, we figured it would be, 20, 30 years away, so many decades away. But on the way there, we think that there's going to be some of the components that we're building for full general AI will be incredibly useful in direct applications in isolation. So we don't think we need to wait for 20, 30 years before we build the final system. We can actually start using the fruits of these algorithms that we're building right now.
When I interviewed you for a Wired cover story just over a year ago, you talked about how you have a 20-year roadmap. How do you plan 20 years ahead when you're running what is still a startup?
Yeah, it's difficult. So we have a long-term roadmap, this 20, 30-year roadmap of some of the big problems we know we need to tackle. But we also have, as we get nearer time, we have shorter timelines too. We have a 5-year roadmap, and we also have 6-month key milestones that we try to achieve. And we try and marry up the short-term goals so that they fit with this longer-term roadmap. And that's another reason that we use games, is that when you're on a very long-term and very ambitious research project, it's very important that you have short-term metrics that tell you that you're going in the right direction with your algorithms. And games, by the fact that they're competitive and they have scores, and we also use computer games, it's very convenient for telling you very quickly, giving you feedback whether your algorithms are improving and by how much.
So you're now part of Google. What examples are we already seeing, or we will be seeing in the next couple of years, of Deepmind applications inside Google services?
So we're working on many things within Google, a whole class of problems you can think of as recommendation systems. So helping improve YouTube recommendations for what to watch next. Also Google Play Store for what app that you might want to install or that you might like to use. The thing that I think is most fun that we've done recently is actually we applied our AI algorithms to the data centers. And we managed to reduce power usage in the data centers by nearly 15% by using these kind of AlphaGo techniques, which of course saves tens of millions of dollars and is also great for the environment.
So that's today, but let's look a bit further ahead. You mentioned using Deepmind's AI to solve some science problems. Give us an example of something you think it could do.
So we feel we can apply this technology to anywhere where there's overwhelming amount of data, and also especially if there's a simulator or some kind of virtual environment that simulates whatever the scientific problem is, and there's a clear objective function, something that you can optimize. So the sorts of things we're looking at actually are, very briefly, is protein folding, for example, which is the proteins are long chains of amino acids. They are very important obviously for human health, and proteins fold up into 3D structures. But we don't know how the 2D structure translates into the 3D structure. But the 3D structure actually is what governs the protein's behavior. And if you want to design, for example, drugs to target certain proteins, you need to know the 3D structure. So what we're trying to learn with our AlphaGo-like techniques is how that translation works. And if we're able to do that automatically, that would be a huge breakthrough.
And you also, how many years away do you think it is before an algorithm writes a credible novel?
I think novels are going to be one of the most difficult things possible, because I think a great novel is also about an expression of the human condition. So I think it will be quite hard for an AI system to write a really meaningful novel in the way that Hemingway can. That would be meaningful to a human being, because you would know that wouldn't have had the shared experience that you've had. So I do actually think that novels and films, it's a very open question as to whether a machine will ever be able to write a meaningful novel in the sense of a great writer.
So when you talk about general AI, there are always certain people that get a bit nervous. They start talking about ethical challenges of the machine taking over, the humans not being able to control it. I mean, Elon Musk, who was one of your early investors, said actually he invested to keep an eye on it. I think the phrase he used is, it's potentially more dangerous than nukes. It's summoning the demon. So answer your critics that you're building something that could act against the interests of humanity.
Yeah, well, just to say, he's building AI himself now, so I think you might want to take that with a pinch of salt. I think there are many interesting questions about the ethical deployment of these systems. And as people who develop those systems and others around the world, we've got to be very cognizant of our responsibilities on that front. And there are some technical open research questions that need a lot more research. But my belief is that these issues can be overcome, and AI will be if it's used in the right way for the benefit of all humanity, then it will be one of the greatest inventions that humans ever made.
I think some members of your team have just published a paper essentially talking about a kill switch for AI, a safely interruptible way of running it. Why would we need a kill switch if it's not dangerous?
So it may not be dangerous. You might want a kill switch to if it's doing things that maybe didn't intend it to do, or that it's doing things in the wrong way. So you always want to have an ability to, of course, have an off switch, and you want to make sure that there isn't any way around that for the AI. So there are many things like that, the devices that are going to be required and invented. But actually, as we started researching this, and over the next few years, next decade, not just us, but academic institutes as well, it turns out that some of these problems are not as difficult as people might have expected.
When you were bought by Google, I think it was a condition of some of your investors that an ethics and safety board was set up. What's it done so far?
Yes, we have an ethics and safety board. That was a very unusual condition we put on the acquisition, and to Google's merit, they were fine with it, and they understood why we wanted it. And the ethics board is basically it's a board that has independent members on it and has veto power over what the Deepmind technology gets used for. We've convened a couple of times. At the moment, it's mostly about educating everyone on the ethics board to get them up to speed with what the technology is and where it might go. Because obviously we have ethicists and all sorts of philosophers and all sorts of people on that board, not just technologists. And so there's nothing yet that's required for the ethics board to sort of pronounce on, but over the next sort of 5-10 years there may be, so we need to get these people sort of up to speed. And we'll be announcing a lot more about that in the next few months, more publicly about what the ethics board is doing and who's on it.
So last night it was reported that a autopilot Tesla, had killed a person and there was an investigation. Should this sort of development worry us?
Well, we don't know the details of that yet, but my view would be that we should probably be more careful about, it's actually a question about testing these systems and getting them out of beta before you launch them on a mass scale for everyday consumers to use. And I think that depending on what comes out of that, we have to wait and see what was the actual technical reasons behind that. It's not clear yet. But I think that self-driving cars ultimately will be a lot safer than human drivers, for sure. So I'm pretty sure that that is, that kind of technology is going to come into play.
So last question before we go into the next session. You've got a team of about 300 now, double the number when I came to see you, based in London. And we're at a moment when all the big tech companies are acquiring all the big AI talent they can find. So it's not just Google, it's Facebook, it's Amazon. Isn't there a danger in all the algorithms creators being inside a few big tech companies? Doesn't it skew the market for startups that actually want to break through?
Well, I'm not sure about that. I mean, I think the big big sort of companies, tech companies, are getting increasingly interested in AI. I think partly because of the work Deepmind's done and others have done. But, actually most of the stuff we do is all published. Almost everything we do is published, and all the tools we use almost all of them are open source. So things like TensorFlow and Torch, which are the machine libraries that we use and build our AI algorithms on, are all completely open source and downloadable. So there's actually more and more tools now for startups to use. And also, I think that some of these technologies, like deep learning, are going to become services that any applied company can sort of implant into their products.
So promise to come back on the Viva stage when you finally crack general AI. Please can we thank Dennis Hasaris and Deepmind.